Hello. A continuous function attains its limit at every point. The graph of a function which is continuous on the entire real line can be sketched with a single stroke. Not every continuous function has a derivative everywhere. It can have sharp edges. Also, such functions may be unbounded. The absolute value of x function has a sharp edge at 0, so it is continuous everywhere, but not differentiable at 0. When restricting a continuous function to a closed interval, interesting things happen. The function obtains its global minimum and maximum, and every value in between, meaning that given the values at a and b, for every c between capital A and capital B, we can find a preimage. This fact is clear when sketching a graph. Its heart is really the following graphical fact. Every curve from A capital A to B capital B must have at least one point of intersection with every horizontal line between capital A and capital B. A special case is when capital A is negative and capital B is positive. Then f must have at least one root. Read the following question. Stop the video now. The answer is 1. Why? If we denote the base camp as height 0 and the top of the mountain as height h, we can sketch the following blue curve as the position of the climber as a function of the time of day, and we can sketch the red curve as the position of the climber as a function of time in the second day. It is impossible to draw those continuous curves without them intersecting one another. This is the well-known definition of the derivative of f, denoted as f prime. By the way, the limit is of the form 0 over 0. Try to solve it using L'Hopital. You would get f prime at x null. Graphically, the derivative is the slope of the tangent line to the graph at a specific point. As with any limit, you need to verify that both one-sided limits exist and equal. And beware from the infinity case, like that in the following example. It happens when the tangent line is vertical, that is, with slope equals infinity. Differentiability implies continuity. The mean value theorem connects between the slope of every second line to the derivative of some inner point. This is the specific statement of the theorem. As a special case, if fa equal to fb, we conclude that the derivative of f is 0 at some point in the interval, meaning it obtains at least one critical point. Graphically, the theorem says that we can move the second line vertically and find a point on the graph for which the line is actually the tangent line. Positive f prime implies f is increasing, whereas negative f prime implies f is decreasing. When the derivative is 0, we may get an extremum point. The second derivative conveys info about whether the function is convex or concave. Positive second derivative means that the function is smiling, and negative f prime prime means that the function is frowning. As I said in the basic module, those word games may sound silly, but they are a good memory tool to whoever English is not his or her native tongue. If f prime prime is 0, the function f may be changing behavior at this point from being convex to being concave, or the other way around. This is called an inflection point. The sine function has one of those at 0 and at every integer multiplication of pi. On the left, we see an example of maximum and minimum points. The following are a few rules for calculating derivatives. Those should be known perfectly. Also, recall the list of known derivatives from the basic module. Note the derivative of a constant a to the power of x. The log a in the derivative is a constant. Remember that when taking high-order derivatives. This is the relation between the derivative of f and its inverse. Example: how many points satisfy this equation? It is a matter of investigating the behavior of x by e to the power of x, which is decreasing for x less than -1, and increasing from there on. At minus infinity, the limit is 0. The function is decreasing until x is -1, and from there, it is constantly increasing to infinity. Therefore, it must intersect the horizontal line of y equals 3 only once. What happens when we do not have a specific formula for y as a function of x, like in the following question? We are treating y as a function and use the derivative formula for the composition of functions. This is called implicit derivative. This is the implicit derivative of the previous equation, and we conclude the following relation for y prime at 1, 1. So the answer is -1. Quiz. Take a full 2.5 minutes for this one. Stop the video now. Ready for the answer? It is B. This is the formula for the volume as a function of r, which is a function of t. Take the derivative as a composition of functions and plug in to get the answer. Note that in the subject math test, with questions like that, we don't really need to be concerned with the units, whether it is inches, centimeters, kilos, pounds, etc. In most cases, you can ignore the units if you found them confusing. More on units in the advanced module. Since it is an important lesson, there is another question for you. Take 2 minutes and stop the video now. Ready for the answer? It is B. Since we are required to find a global maximum, we have to check the endpoints, which are the global minima in this case. This is the formula for y, and we need to maximize the value of xy. X is positive, so we are allowed to put it inside the square root. However, since the square root is monotonic increasing function and continuous, it is sufficient to maximize this and avoid complicated derivatives. This parabola is easily sketched, and the maximal value is when a is 1 over 2, meaning x is 1 over square root of 2, which gives us the final answer. Remember to go back to the original formula for the area before all the manipulations were made to ease calculation.